All right, today we're going to wrap up our chapter 7, which was on waves. And so our last topic is what we call resonance, and it just has to do with things that are oscillating, like whether it's a pendulum or a spring or anything that's sort of vibrating back and forth or moving. We can actually add amplitude to that motion, and it can cause certain things to happen. So let's go through a little bit of the theory first. So we can get some cool things happening. So a good example is, imagine a pendulum, like a kid swinging on a swing, and you want them to swing higher. So to push a kid on a swing, you're not just randomly pushing whenever. You're trying to time it just right so that when they come back to you, they make that one full period, that's when you're adding energy. So if we add the right amount of energy, we could actually keep that kid swinging forever, right? If we just cancel what's lost due to friction, we could just keep adding that, and it wouldn't take too much to keep that kid swinging. If we wanted to make them swing higher and higher, we just would add more energy each time they made the one full swing or when they made the one period. And if we add it at the right time, if we do it in sync, we can actually get that thing moving bigger and bigger and bigger. We can keep increasing the amplitude, and that increase of amplitude is what we basically call resonance. So anything that's oscillating will have a resonant or natural frequency. So if we take a pendulum that's 1 meter long and we swing it, it's going to have a certain period or a certain frequency. So if we match that frequency, so for example, if we had a period of 2 seconds, the frequency, remember, is 1 over. So the formula from frequency to period is just the flip of it, the reciprocal. So if we have a total period of 2 seconds, that means every half a second it's going to make, so it'd be one wave in a half a second, or per time. So then if we time it just right so that we're pushing on this thing every half a second, we can get this thing to swing bigger and bigger. So if we just left it, if we push it once and leave it, it's eventually going to stop because of friction, air resistance, things like that. So if we can match that energy that's lost, so we don't have to actually put that much back in, we just need to basically overcome whatever it's losing, and that would keep it swinging over and over again. So that's why when we push a kid on a swing, we can actually do it pretty easily. Once you get him swinging, you're not really doing that much. You're just sort of adding a little bit of a push each time to overcome what was lost due to friction. But, so that's the resonant frequency. So everything that moves, so if you think of a spring going back and forth, it has a certain period or a frequency. We can measure it to whatever we want, depending on the mass and the spring constant and all that kind of thing. Or if it's a pendulum swinging, or what we're going to see, it actually works for anything. Anything that has sort of a pattern to it, like a vibration to it, we would say that has a frequency. So sound, we could have resonance in terms of sound. We could have resonance in terms of light. Anything that vibrates, like a drum or a musical instrument, or even just a piece of paper that wobbles back and forth, anything like that. So what we call mechanical resonance now is if we actually add energy at the exact same frequency, we can not only just overcome what's lost to friction, we can actually make it bigger and bigger. We can increase that amplitude, and it doesn't take very much. So, and if we get large enough and the object can't withstand that amount of energy, we can actually get things to break apart or destroy themselves if we add too much energy. So a simple example is if we just keep pushing on that kid on a swing, we keep pushing higher and higher, eventually we push them right off the swing, right? It'll swing all the way around, or it would even just swing up high enough where the kid would fall off or whatever. If we were to add energy on something that's not movable, like a spring or a pendulum or something, that's when we start running into issues. So this is an interesting story about legend, and what this basically is saying, that in the old Roman Empire days, the soldiers were marching and they were going across a bridge, and they were marching, so they're doing the whole left-right thing where everybody's marching in sync, and basically that left-right, once they got on the bridge, they were actually causing vibrations in the bridge, and because they were all doing it at the same time, they were all doing it in resonance, and it happened to match the resonance of the bridge, natural resonance. And basically what they said was the marching alone was enough to cause the bridge to start to bounce up and down, and because it was made out of bricks or whatever, it collapsed and all the soldiers fell into the river and died. So it's kind of a weird thing, but obviously there must be something to it, because if you actually go to this bridge in Europe, this Albert Bridge, they actually say that all troops must break steps. when they're marching across the bridge. So they obviously something's occurred and they don't want that resonance to happen. So that's just a simple example. You guys have all probably seen videos, or if you haven't, look on YouTube. We'll look at some in class. But this first title page, we got this wine glass shattering. So if we match the resonance of the glass, even though glass you would think is solid, but we can get it to vibrate, and if we can get it to vibrate enough, the glass isn't strong enough and it shatters. So if we can match the resonance of the glass, we can actually shatter a wine glass. When you hear stories of like opera singers or something like that breaking glasses, it is indeed true. All they got to do is hit the right frequency. It doesn't have to necessarily be loud. It just needs to be the right frequency to add that energy. And probably a most famous example in history is the Tacoma Bridge. So if you Google or do a YouTube search of Tacoma Bridge collapse, this happened in about 1940 or so. And what happened was they made a suspension bridge to withstand the weight of the cars and things like that, which worked great, except it's a pretty windy area, and the wind was blowing across the bridge, kind of like when you blow on the edge of a piece of paper. It started to make waves on the bridge, and because the wind and the frequencies matched enough, the waves kept getting bigger and bigger and bigger, and eventually the bridge broke apart because it couldn't withstand that amount of energy. So the video will show this bridge collapsing in real time, and it's pretty cool to see. And you can do all kinds of resonance searches. So you could do it with water waves, right? You bounce the waves and you time it just right so that the waves get larger and larger. Anything, basically any kind of frequency, anything that has period or frequency, if we can match that, we can actually create resonance. Another good example would be like a noise you hear in a car. You drive down a road, your car's pretty quiet, you hit a certain speed, you hear a rattle in your dash or a vibration or something. What you're actually hearing is resonance. The car is vibrating and it's hitting the right frequency that we can actually hear it. You go a little bit faster, maybe that rattle or squeak goes away. So those kind of things are all just examples of resonance. And that's it for this chapter.